So we're going to begin first with sets and cardinality. So just some like basic front information before we do examples. Remember, a set is a collection of objects. And there are two aspects of it. Number one, order does not matter. And then number two, no duplicates. Right, so no duplicates in a set. We only have one of those objects, right? So that's what a set was. We can describe a set using many different ways, either using what we call like roster building notation, intervals, the curly brackets, or we can just describe it in words. But for the most part, we're going to look at just kind of the curly brackets or either that or just describing them because they're too big to be able to do that, right? And then we have three major set operations. So the first one was the union. So that's going to be A union B or A or B, right? Which is an element in A or B or both, right? And if we draw that as a Venn diagram, if this is A and this is B, then the A union B is just all of that shaded in like that. So A union B, right? So that was the first one. The other one is the intersection. So that's A intersect B or A and B. So the and is the word for that, which is an element in A, sorry, both A and B. Okay. Let me make it, which is all elements, and which is all elements in A or B. So from the Venn diagram perspective, that's not any better, but that's okay. That's just going to be like this little region right here. So A intersect B. And then the last one was the complement. So the third one, the complement. So A prime or AC, which is all elements not in A, right? So if you draw like a little box that represents everything, and then you draw a circle, give you A and B, and this is A, then everything outside of the circle is the complement. Like that. So that's AC, right? So those are the major three. Do know those because they are important. And then from that, we talked about cardinality, right? And these pictures that I've drawn right here are called Venn diagrams. So this is a Venn diagram. And then the square is called the universal set, which is basically the big set, the one that contains everything. So thankfully, its name is very descriptive of what it does. So let's just do an example. Well, actually, I got to define cardinality first, so let's do that. And then the last thing, the last major thing was the cardinality. Actually, you know what I can do? I can do this. Let me make this. Put that right there. And then I could just all have this on one slide so it looks a little bit nicer. Okay. Yeah, so the cardinality of a set is the number of elements in the set. And so the way we abbreviate that is N of A. So that's kind of the notation that we use. The number of. So you can think of the letter N as the number of. I mean, it's kind of that literal in a way. So that's the cardinality, right? And those are the main things that we talked about. There's like one little other thing, the formula that we'll talk about afterwards, but the first thing that we want to be able to understand is just, finding sets and finding the cardinality, okay? Most of the time, what they focus on more is the cardinality, just because that's just typically what they like to focus on from my experience. So here's an example. And this is straight from the review. So this is actually number 15. So the first question that they ask is, what is the cardinality of A union C? So that's the first question. And if you notice the screen is going gray, that's just me screen clipping, so it's nothing on your end. Okay, so with this problem, first thing I would do is find A union C. So let's just find what that is, right? So remember, union means or, okay? And let's write this over here. If you're doing a union, sets get bigger. Sets get bigger. And then for intersection, sets get smaller. Like that. And then for complement, there is no rhyme or reason. It could be one or the other. So A union C. So I like to stack up my sets. So we write the names down. And then C. One thing is make sure that you actually look at the correct letter. Like that. Okay. And then we want to find the union. So the union is basically just adding the sets together and then getting rid of the duplicate. That's actually kind of what you're doing, although I would not say that officially. We're just going to combine them together. So I just go one by one. So Dirk, Franz, Johann, sorry. And then I go to the next set. So done, 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 done. I already used Franz, so no. And then Tina. So I write down Tina. Okay. And there it is, right? So that's the union. And then step 2 is just count now. Count for N of A union B. So N of A union B is equal to 1, 2, 3, 4, 5. So 5. And there we go. Any questions on that? All right, so the next example that we're going to do is this one. So this one has the complement in it, so we'll have to take that into consideration. So step 1 is to find, so first I would find the complement. So find B complement, right? And so in order to find B complement, right? So the complement is always relative to the universal set. So S right here is the universal set. That has everything. So B is B, and then B complement is everything that's not in B, but in the universal set. So if I were to write down B, okay, so I'm just writing it down. Again, you don't have to do this, but that's going to be Franz, Enrica, Claus. Sorry. And let me give myself a little bit more space. Tina. Okay. And then the complement is just everything that is not what I have above me. Okay. So if I look at the universal set, I have Arthur, right? So Arthur is allowed. And just to like make this, I guess, as obvious as I can, I'm gonna copy this over right here. Okay. And I'm gonna paste it relative to ours. So right here, we're comparing that to B. So Arthur, good. Dirk, good. Franz, nope. And then Henrika, nope. Johann, yes. Claus, nope. Sorry, nope. Tina, no. So those ones don't work because I already have them in B. And remember, B complement is everything not in B. So that's the key. Okay. So then step 2 is to find the intersection of A and B complement. So A is equal to, well, it's Dirk, Franz, Johann, and sorry. And then B complement is just Arthur, Dirk, and Johann. And so when you do the intersection, your set usually, there are cases where it doesn't, but most of the time, it will get smaller. So if it gets smaller, because they don't always share the same thing, right? So they both share Dirk, so I'm just going to highlight that for you. So Dirk, actually, I'm going to use a different color. I liked blue today, so we'll do lavender. Dirk, Dirk, and then Johann and Johann. Those are the only ones that they share. So I do Dirk and Johann. And then step 3 is to count for the cardinality. Oops, wrong symbol. And so we get the intersection of these two is 1 and 2, so 2. And that matches my answer. So, yep. Okay, so doing the last one. And so one thing to remember is that when you're doing set operations like these, order of operations is still in place. So you do the inside of a parentheses and work your way out. So for this one, what is the cardinality of A intersect B complement? So I am going to first find the intersection and then find the complement of the intersection. Okay. So I'm just going to copy the sets over so I have them right there. So let me copy this over. So A and B, like that. And so step 1 is going to be to find A intersect B. So you do basically an order of operations. And so because it's an intersection, all you have to do is just find out which ones overlap. So just highlighting. They don't have Dirk. They both have Franz, like that. Don't have Johann, and they both have Sorry, right there. So those are the two that they share. And so A intersect B is equal to Franz and Sorry. And then step 2 is to find the complement of that. So A intersect B, complement. Okay. Now, fun fact, there actually is a way of distributing that complement, and it actually has a name. It's called De Morgan's law. So he was a famous mathematician in set theory, and he actually figured out a way of distributing the complement. So if you wanted to, you could actually do A complement union B complement. But the only reason I wouldn't recommend doing that in this case is because then you'd have to find the complement of 2 sets and then find their union, which I think is more work. But theoretically, you could distribute if you wanted to. Okay. So there is S, and then our intersection is A intersect B equal to Franz and Sorry. And so the complement of that, so the opposite, is basically don't want Franz and don't want Sorry. So everything else is okay. So Arthur, okay. Dirk, that's okay. Franz, nope. Henrika, that's okay. Johann, that's okay. Claus, that's okay. Sorry, whoops, let me put check marks on these. So Franz was not okay, Henrika was, Johann was, Claus was. But sorry is not okay because we already have it in our other set, and then Tina is okay. And there we go. So now we have the complement, and then step 4 or 3 is to count. And if you think that the amount of work I'm showing here is too much, that's fine. Because technically, some people can see it a lot faster than others, and that's perfectly fine too. So, do as much work as you need for yourself to be able to convince yourself like that's the correct number, right? So, 1, 2, 3, 4, 5, 6. So the cardinality is 6. Like I said, some people could be like, okay, A intersect B. So I got Franz and Sorry. Those are the only two. That means the complement is everything but that. So that's 1, 2, 3, 4, 5, 6. That's the answer, right? Like you could do that. It's just some people aren't as good at seeing the sets like that. So writing them out is very helpful. So we're going to do an example from the homework. I'm just going to change the number to make it a little bit more interesting. So determine the cardinality of the set of all the outcomes of rolling 2 distinguishable dice that add up to, let's do 6, okay? So here you have to think about it just a little bit more logically. So step 1 is find your set. So find set. And you can call it whatever you want. We'll just call it A, find set A. Oh, they call it E. So E is going to be equal to roll a 6, which means because they are distinguishable, that means 1 comma 2 does not equal 2 comma 1. Those are different, okay? Because one may be blue and one may be red. If they were indistinguishable, 1 comma 2 would be equal to 2 comma 1. So that's the difference between distinguishable and indistinguishable. It's like when you play a game, if you roll 2 white dice, you can't tell if they like rolled too much, which one was which originally. But if you roll a red one and a blue one, you can always tell which is which because one is red and one is blue. So they have to add up to 6. So the first one I think of is 1 comma 5 because 1 plus 5 is 6. Then 2 comma 4 and then 3 comma 3. Okay. And then I think 2 comma 4 and then 1. Sorry, I already did that one. 5 comma 1. Okay. And then so I got 1, 2, 3. I need 4 comma 2. Actually, I went the wrong way. So 4 comma 2 and 5 comma 1. So I got 2, 4, 4, 2. Actually, I did that one twice. That's why I confused myself. 4 comma 2 and then 5 comma 1. There we go. I wrote the same one twice is where I messed up. Okay, so do I have all of them? 6, 6, and 6, and 6, and 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yep, I have all of them. Now, if you're wondering, why is there only 1, 3, 3? Because there's only one way you can roll a red 3 and one way that you can roll a blue 3. So 3, 3 is the only one that doesn't have it twice. And that's the same for all dice. 1, 1, 2, 2, 3, 4, 4. All of those, they only have one roll. Okay? And then now we just count. Step 2 is to count. So the cardinality of E is equal to 1, 2, 3, 4, 5. So it's just 5, right? So one thing that you're going to have to be careful of is you're going to have to read the problem. If I ask for a probability, that's where you're going to divide and give me a fraction. If I ask for like a cardinality, I just want the number of things in there. So one very important thing is like, because I've seen people where they think it's a probability problem, but it's actually like a cardinality problem. So just make sure that you pay attention to that. Okay. And then one last thing. So here's another example. Let A be equal to 1, 2, 3, and 4, and B be equal to 5, 7, and 9. Okay, find the intersection of the two. If you try to find the intersection of two sets and they do not share anything, then we call that empty. So they don't have any numbers together, so it is empty. So the empty set. The word that we actually use is called mutually exclusive. They do not overlap on the Venn diagrams. All right, so the other big topic that was related to 7.1-7.2 was the principle of inclusion-exclusion. Apparently, it has an abbreviation, which is just PIE, so PIE, principle of inclusion-exclusion. And all that says basically is like if you're trying to add up how much you have of something, specifically if you're trying to find the cardinality of the union of two sets, okay, then effectively you just add up everything you have in A and you add up everything you have in B. But the problem is if they overlap, you've basically added up too many things. You've double counted, which in counting is like the most bad thing you can do. It's like the cardinal sin of counting. We got to subtract out where they overlap, right? So effectively, if you draw like a Venn diagram and you draw A and you draw B, if I count all of A right here, and then I count all of B right here, the problem is you've counted that middle region twice, so we have to subtract out the double counting. That's what that formula does. It just subtracts out the double counting, which is really important, right? And so generic problems I can ask you is like, I can just give you part of the formula and you tell me, hey, what is the missing part, right? So this is an example from the review. So let's do this one. So step one, write down the formula. And so a question you might ask is, how do I know to use the formula? If you just see like this and this, that automatically means use the formula. Is there any other formulas that you need to know for this type of problem? No, there isn't. You could do it for bigger sets, but that we're not going to do that in this class. But in case you were curious, if you wanted to do it for 3 sets, and I'm just going to show it to you in the video, but not leave it in the notes, that's what the formula would look like. It's just you have to add up all of them, and then subtract out where they overlap like 2 circles at a time. But then the thing is, you actually subtract out too much, so then you have to add back in the little tiny part where they all overlap back in. So that's if you want to do 3. And then there's actually an even larger formula if you want to do it for like 20 sets, or like you can just keep going forever. But that formula you don't want to see; it's too complicated. So we use our formula. Minus the intersection. Key thing is just don't get these mixed up. Like don't put the union and the intersection backwards. I've seen people do that. Just got to memorize the formula. And then step 2 is just to plug in, right? So we just got to plug it in. So plug in. So they told us this right here, right? So 80 is equal to 50 plus 40 minus the intersection of A and B, right? So just simplify. And so we get 90 minus the intersection of A and B. And so I could subtract over the 90. And I get -10 equals negative n of A intersect B, the number of A and B. And then divide by -1, because they're both negative, and then there it is. One thing to note, and this is very, very important, and I'll write this at the very beginning. Okay, where is it? Cardinality. Actually, I'll note right here. All answers will be positive. And not fractions. So if you're doing cardinality, you have to get a positive number and it can't be a fraction. So basically a whole number, including 0, which the whole numbers does. Okay, so that's the nice thing is your numbers, they always work out nicely. They can't be anything bad. So there is a problem kind of like this in the homework, but we also did one in class just like this, and I think this is just a good problem. I'm going to probably do 2 of these. So basically what I'm asking you to do is just like figure out how many are in A or B here. So I want you to use this formula, but I am not going to actually tell you which one is which directly. You kind of have to figure out what it is, right? So step one is first just find, write down the formula. So if you're talking about cardinality and you see the word or and, you automatically want to use this formula because it's the only formula you actually kind of have at this moment and pretty much for the entire exam of cardinality. Like this is the only one that you can use. Okay. And then step two is I would draw a Venn diagram now. So a Venn diagram. So your Venn diagram will have a box. So that's going to be everything. And then we call that S for the universal set. And then we're going to have two circles, one here and one here. Okay. And so from there, we just need to figure out how much each circle has, each little region, right? So we're going to call this A and we're going to call this B. Okay. And that's the basic principle. And so I'm just going to make this bigger just so that I have more room to write. Okay, like that. And so they tell me that set A contains 304 elements. So A, the cardinality of A has 304. Okay, that's what they tell me. And they tell me that B, okay, the set B contains 448 elements. So the set B is equal to 440, right? And they say if set A and B have 61 elements, so that you see the word and, that means this little region has equal to 61, okay? Do you have to draw the Venn diagram? You actually don't. This is just helping you visualize what's going on, right? So this is A and this is B, and then that's the intersection of B, okay? Actually, I'm not going to put it in there because that could be a little nuance. And then step three is to plug in, okay? So n of A or B, right? So they say, what is the total number in A or B? And so we plug in 304 plus 448 minus 61. And if you plug that in correctly, you're going to get 691. Okay. And that's it. So you might think, is the Venn diagram necessary? No, in this case, it's actually not. But there are problems where maybe I want to know how many elements are just in A, right? So like, what if I wanted to know, so this is like a follow-up question right here, B, how many elements are just in A, right? How many are just in A? Well, I know that A, so the cardinality of A is equal to 304, right? But that's the entire circle. If I want to know just A, so that would be like this part of the circle, okay, I would have to subtract out where they overlap. So then the shared elements is equal to 61. So only A is equal to 304 minus 61, which is equal to 243. So this is 243. This is 61. And then if I wanted it for B, okay, so then I could do 440 minus 61, and that would be 300 and let's see, 79, right? So that's how many elements are in each little circle, right? Again, maybe a problem doesn't ask you to do that, but in the event that they do, they could. And so here's a great question that I think kind of reinforces the use of the Venn diagram. Okay, so we're going to do this example. And then we'll see if there's any other ones that I want to do, and should be good with 7.2, 7.3, 7.1, 7.2. So the Phoenix School District services the elementary and middle schools in Phoenix. 32 teachers are teaching in Phoenix, and 83 are teaching in middle school. Sorry, first was elementary, second was middle school. If 12 teachers teach at both, what is the total number of teachers employed at the district? So I just want, how many total teachers are there, right? So step one is formula. So N of A union B equals n of A plus n of B minus n of A intersect B, right? And then step 2 is a Venn diagram. Another thing the Venn diagram helps you do is it also just helps you label things. So that way, when you're drawing it, you know what is what. So this will be elementary, and this will be middle. So I am told that elementary has 32. So this big circle is 32. I'll just write that elementary. And then this is middle. And so middle school is 83. And then if 12 teachers teach at the school district, that at both, I have 12, right? And so what a student could do accidentally, and this is the reason that I mentioned this. So I'm going to do n of E elementary, and then n of M for middle, is they might just add up all the numbers together. But if you just add up all the numbers, the problem is you've essentially double counted because there are 12 teachers that teach both, right? So again, you don't have to do this, but could there be a question maybe on the exam where they're like, fill out the Venn diagram? Because we did have an example of that on the homework. Sure. So this is what we're doing. We're just filling it out. So 32 teachers taught taught elementary. Now, here's something important because this comes down to English and logic a little bit. If I say 32 teachers teach elementary, they could also teach other things. The only condition for that statement to be true is that they're teaching elementary. So this part of the circle right here that I've outlined is the teachers that only teach elementary. So if you do 32 minus 12, that is 20 teachers that only teach elementary. Okay. So this right here is only elementary. And then 83 minus 12 is 69. And so that's only middle school. And then from there, we can just plug into the formula. So plug in. So you could do it two ways. You could add up the 20, the 12, and the 69. So I could just do that. But if you just plug it into the formula, okay, so what is the total number of teachers employed? So it would just be this, which is equal to 32 plus 83 minus the 12. And if you add those together, what you're going to end up getting is 103. Or you could add up 20 plus 12 plus 69, and that too is equal to, did I do that right? 103. All right, let me make sure I'm looking at the right problem. Okay, I noticed my mistake. It's you're probably watching the video like that. Isn't that wrong? No, it's 71. That's where 71. So a different interpretation, right? As long as you're not double counting, you can add things up. So that's one way of doing it. But fundamentally, the formula takes care of it. So that's why we like this formula, because I don't have to think about it that deeply. As long as I know how much is in one set, how much is in the other, and how much they share, the formula will always take care of it, right? But what I want to show you from this example more than anything is just how to set up a Venn diagram too, right? Any questions? So when it comes to this problem, my recommendation is probably just use the formula. But if the problem requires you to use set up a Venn diagram, then you could use the Venn diagram to your advantage. But ultimately, if you want to just take the path of least resistance, just use the formula, plug in the numbers, and you're good to go, right? So the formula will always take care of it. Just in the event that they do ask you a Venn diagram problem, I want you to be able to use it and utilize it. Okay, so here's just one more Venn diagram problem. This was kind of like similar to the last homework question, but they just gave you a little bit more information. This one is just, I give you all of the information that you need. And so all you have to be able to do is just fill out the Venn diagram. So I would probably just label these as like science, history, and psychology, right? And so the key here is just work inside out. So work inside out. So first determine how many students took all three classes. So I see all three classes right there. So that's going to be 280, right? Because they all took three classes, right? And then from there, you're going to now do these right here. You're going to basically look at the intersections of two of them. So history and psychology right here, history and psychology. So that's going to be this one right here. And I am told that these two have to add up to 563. So 563 minus the 280 that already have taken both, right? Let me just make that a little bit easier. So 563 minus 280. That's going to be equal to 277. And I'm going to verify that before I continue. That does not look right. So let me just do it. 563 minus 280 is 283. So not even close. 283. So those are the students that took history and psychology, but not science, right? So that's what that means. Okay. And then they tell me, okay, the next one is history, sorry, science and history. So that's going to be this one right here. So I know that 638 students took science and history, but I have to subtract out the 280 that took both. And so if I subtract those two, I end up getting 358. 283. Actually, let me go back to my color. And then I just keep going, right? I just keep going in this circle. So then we go to the next one. And so the next one says, okay, science and psychology. So that's going to be this one right here. So we do science and psychology. So 675 minus the 280. And we get, so 675 minus 280, 395. And there it is. And then now I know how many students took science, history, and psychology. So I'm going to use all of those numbers, right, to basically find science, history, and psychology only. Like they only took a science class, they only took a history class, and they only took a psychology class. So science is going to be equal to 1351 minus the 358 minus the 395 minus the 280. And if I calculate that correctly, you're going to get 318. So 318. And then if you do history, that's going to be 1140 minus 358 minus 283 minus 280. And so if you do that correctly, you're going to get 219. Okay. And then the last one is psychology. 1326 minus 283. I'll do 395 minus 283 minus 280. And if you do that one correctly, you're going to get 368. Okay. Now, if I add up all of these numbers, so if I sum of all regions, that would be equal to, so you add up all of them, you're going to get, let me find it real quick. It's in the problem statement. They tell you that it's 2427 right here. And then if you want to find out how many students took none of the classes, sorry, so we already know how many all, so none would be equal to 2427 minus, okay, Actually, no, I apologize. We know how many total students took it, so total that took class, so total that took class is equal to sum of all regions. So I was right. And if you give me 1 second, I will calculate that. So it's going to be 2, 2, 2, 1. So basically that's all of the circle regions added up. And then if I want to find how many students took none, that would be 2, 4, 2, 7 minus 2, 2, 2, 1, which is equal to 206. So the actual number of students who did none of the classes, they didn't take history, psychology, or science, there's 206 students like that. So if you feel comfortable filling out this Venn diagram, then you've mastered the Venn diagram, right? So then I could just ask you questions like, well, how many students did history or psychology? So history would be this circle, or psychology would be this circle. So then I find where they overlap, and I just add those two numbers together, and that's my answer, right? So do I think they'll ask you to do a 3 Venn diagram on the exam? No, because honestly, it would just take too much time. But a 2 Venn diagram, sure, that's always plausible. If I gave you a 3 Venn diagram, I'd probably just fill out most of it, if not all of it, and then you could use that to answer questions if necessary. All right, so let's talk about counting techniques. So the first thing that you want to understand is the difference between the addition principle and the multiplication principle. So when it comes to the addition principle is all about combining events that are kind of separate, like they're disjoint, we would say. And then multiplication principle is all about looking at how many ways can things happen if I do them in a sequence, right? So the key word, honestly, is sequence here. So the addition principle is basically this. Let E1 and E2 be, we would say, disjoint events, meaning they have no overlap. There's no overlap between them. So nothing in common. So let E1 and E2 be disjoint events, nothing in common. And E1 has M outcomes, and E2 has N outcomes. Okay. Then the total number of outcomes for E1 or E2 is their sum, M plus N. That's it. And so basically, this will happen when you're trying to essentially look at different things at the same time. So, for example, when we were looking at the outfit example, I made the comment that when you're finding an outfit, you're going to use the multiplication rule to basically figure out, an outfit for a shirt. But the thing is, if you have more than one shirt, you can't wear the same shirt. You can't wear 2 shirts at the same time, essentially. So each shirt is separate from the other shirt. So at the end of all of it, we add them up together. So that's kind of the basic idea. But let's just do a very simple example. Okay. You have a choice of 5 beef dishes and 8 chicken dishes. How many options do you have? So I didn't ask you how many ways can you eat a chicken or beef dish. I just asked you how many options you have. And that's really what the addition principle is all about. It's just like, how many things do you have to choose from in total? right? Well, it's just 5 plus 8, which is 13. So that's like my total options. So when you're doing some of the multiplication rules, like, problems, you first actually have to use addition to set it up, right? Like, how many letters do I have? How many digits do I have? How many, options do I have? That's the addition principle. It's just taking all of your options and then start to multiply them or pick them or order them, right? That's kind of the whole idea. So now we're going to talk about the multiplication principle. So the follow-up to that is the multiplication principle. And this is the one that you're actually going to use the most, but I will show an example where you combine the two because sometimes you have to, right? So the idea here is let E1 and E2 be events with M and N possible outcomes, respectively. Then the total number of outcomes for a sequence of two events, E1 and E2, is M times N. Okay? You just multiply them together. So let's just do some examples. And again, sometimes there are so many like fancy ways that you can do this, but also you want to sometimes just think about it in the simplest way, right? So I'm just going to grab a random example from the internet just to illustrate this right here. So suppose there are 3 major auto routes from Washington, D.C. to Chicago and 5 from Chicago to Los Angeles, right? How many routes are there, right? So how many routes are there? Well, again, it just kind of depends on how you want to interpret this, but effectively, I just want to find out how many routes are there from DC to Chicago, and it's just we're going to multiply, right? So if you're going from Washington, DC to Chicago and then Chicago to LA, so basically you can think about it this way. So again, there's several ways you can do this, but if you do DC, then you have 1, 2, 3, and each of these routes will take you to Chicago, right? So Chicago, Chicago, and then Chicago, right? And then each of these will have 5 routes. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and they all take you to LA, right? So if you add all of the different routes, so route 1, route 2, route 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, you add up to 15 routes, right? So, or how many ways can you get from DC to Chicago? Well, there's 3 ways. And then how many ways can you get from Chicago to LA? Well, 5, right? So 3 times 5 is 15 routes, right? So that's effectively what I'm asking. How many ways can I get from one place to the next place? And then I have all of these different ways in between. So then you can make these a little bit more challenging because I can start adding restrictions to you, okay? So, for example, in this problem on the review, we say, okay, you're going to eat a meal consisting of an appetizer, a soup, a main course, and a dessert. There are 5 appetizers, 5 soups, 6 main courses, and 6 desserts. Your diet restricts you between choosing a dessert and an appetizer. You cannot have both. Given this restriction, how many 3-course meals can you have? Okay. So if we count, there is 1, 2, 3, 4 courses, but they ask for a 3-course meal, right? So using that, like I say, I like to, set up the little hangman. That's what I call it. I don't have any other way of calling it. So 1, 2, 3. So this is course 1, this is course 2, and this is course 3, right? Now here's the cool thing. It doesn't matter in this case if I eat dessert first or soup first or anything like that, but you'll kind of want to just follow in line of how they word it. That's typically just the most intuitive way, right? So first thing is I'm going to eat an appetizer, but the thing is, if I want to eat an appetizer, I can't have dessert. Okay, but if I want to eat a dessert, I can't have an appetizer, right? So then what you could actually do is this. You could say like, well, if I can only eat one of them, then they're essentially all the same thing to me. Like an appetizer and a dessert are the same. So you could put it in course 1 or course 3, but we could just say this is going to be your apps plus dessert. Okay, because they're effectively all the same because they're all unhealthy for you, right? So effectively course 3 is my unhealthy option. So if I take the number of appetizers and the number of desserts, which is 6, I have 11 options, right? And then for my soups, I have 5 options, so soup. And then for the main courses, I have 6. So 5 times 6 times 11. And if I multiply those all together, I should get 330. Yep. So 330 meals like that. And so that is the interpretation. So then this kind of idea leads into permutations. Okay, so we can start talking about permutations and the fundamental theorem of counting. And the fundamental theorem of counting, honestly, is just the multiplication rule. It's just, we can go further than that, right? So if you have n options and no repetition, okay? So you have n options and no repetition. Actually, there's one other condition too. So n options, no repetition, and all items are unique. So there's a difference between repetition and being unique slightly, because it's just a way of describing it. So all are unique. Then the number of ways of ordering n objects is n factorial, right? Which is just equal to n times n minus 1 times n minus 2 dot 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 3 times 2 times 1. So this is assuming that you're ordering everything. Okay, so that's why we call it the fundamental theorem of counting. You can just order everything. And then permutations is like, well, what if I don't want to order everything? Like I want to order some things, and that's the permutation. And then permutations can be expanded to just cover everything too. So a quick example, how many ways can you order 5 books? Okay, how many ways can you order 5 books? Well, if you are ordering all of them, then it would just be 5 factorial, which is 5 times 4 times 3 times 2 times 1, right? And that would be equal to, I believe it's 120, but I will double check. 120, yeah. But you could also just think about this in terms of the hangman game, right? So this is why I like doing this, because for most problems, it works out pretty well. How many books am I ordering? So you can do, or I have 1, 2, 3, 4, 5 books, right? I have 5 books. And then I ask myself, how many options do I have for the first book? So I have 5, right? First book. And then once you use a book, that book can't be in another spot because it doesn't exist in 2 different locations. There's no repetition, and that book is a unique book. There's no other duplicates or anything like that. So then I have 4 options for my second book, and then I have 3 options for my third book, and then I have 4 options for my, sorry, 2 options. I looked at the wrong number. And then I have 1 option, right? So as you're going down the line, you're starting to lose more and more options like that, okay? And then if you multiply all of these together, you get 120. And so the nice thing about this strategy is it basically takes care of permutations, because if you think about it in terms of permutations, you're going to have to remember that there's a formula to it. And I always tell students that formula, you don't really ever have to use it because you can kind of reason it out just by doing this, right? But we'll remind you of the formula just in case you want to use it. So with permutations, if you have n objects and want to order r objects, then assuming no repetitions and unique items, the number of ways of organizing our objects from n total objects is, so the notation that you're going to see the most is NPR or NPK. So it's going to be n factorial over n minus r factorial, like that, okay? And then it is also multiplied by r factorial, like that. Nope, no r factorial. That's combinations. One step ahead of myself. So n minus r factorial. There we go. So that's your permutation formula. And if you're wondering, like, what does that denominator actually mean? Well, the thing is, it actually basically gets rid of the part of the factorial you don't need. Okay, so when you do the factorial, you have to do all of them. So if I want to order 5 books, then I have to use all 5 books, right? But what if I only want to order some of the books, right? So I don't need the third option, the second option, or the first option. So that's what the n minus r factorial does, right? So essentially, here's an example. How many ways can you order 4 books from 10? Okay. So again, if you just play the game that I've shown you, well, how many books do you have? 10. How many books do I actually want to order? I want to order 4 of them. So 1, 2, 3, 4. I only need 4. So then how many options do I have for my first book? I have 10 options. I've used the book. How many options do I have left now? 9. Okay, I've used the book. How many options do I have left now? 8. How many options do I have left? 7. Okay, so you can't do 10 factorial because 10 factorial would go all the way to 1. So effectively, okay, so the answer to this question is just 10 times 9 times 8 times 7. So 10 times 9 times 8 times 7. And we get 5040, 5040. So the formula says, okay, if I use the formula, it would be, so using the formula, 10 factorial over 10 minus 4 factorial, like that. So if I write out 10 factorial, that's actually not a very good way of writing it. Let me do dots. They look like a bunch of polynomials. Right? And then this is 6 factorial, so 6 times 5 times 4 times 3 times 2 times 1. Well, these all just cancel each other out. And what are you left with? 10 times 9 times 8 times 7, which is what we have right above, right? So that's what the formula is doing. It's just cutting out what you don't need. I don't need all 10 books to be organized. I just need the first 4. So how many options do I have for the first 4? I have 10, then 9, then 8, then 7. So I always tell students, you don't ever act, so like if you ever actually use this formula, like you use that formula specifically, you're kind of doing it incorrectly. You should never have to use that formula, like the factorial formula, because you can usually reason it out yourself or use a calculator. So never ever actually calculate the factorial yourself. Just use the NPR calculator. And so if you don't know how to do that, it's very simple on your calculator. I'll show you very quickly. So let me grab my calculator. So let me go to, so here's my calculator. You're going to do second quit. So if you have a newer calculator, you should do this no matter what anyways. So the first number, n, is your total. And then this is what you have picked, right? So it's your objects, whatever you pick. So for me, it's going to be 10. So you have to type in the number first, your total, hit the math button, and then go to PRB for probability, and it's the second option right there. And then NPR, and then 4, right? And then 50/40, right? Or 10 times 9 times 8 times 7, 50/40, right? Same thing. If you have a newer calculator, yours might show up as like the actual P. But if you go into PRB and you just type in NPR immediately, you're going to get this A and S because it's just taking the last number that you had in the calculator as your placeholder. So that's why I tell students you need to type in the number first before you use this command. Otherwise, it's not going to like it. Okay, so that's how you do NPR. All right, so that's permutations. Kind of went out of order, I realized. So this is the permutations of all objects. Okay, so I'm actually gonna write that here. So this is the ordering of all objects. And then I'm going to put in parentheses, no repetition. So it is a permutation, but a permutation of everything, right? And then this is permutation. So some objects, no repetition. And then the one that I skipped over, which I'll just do now, is the ordering of repetition. Okay. So what happens when you do have repetition? And this is like the actual like fundamental principle of ordering. It's just like there is no restriction. So basically, here is no restrictions. So let's do an example from the review. We'll do the first one. A 6-digit password is formed from the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. How many different passwords are possible if digits are repeated? Okay. So again, we want 6 digits. So 1, 2, 3, 4, 5, 6, right? That's it. And then how many digits do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 digits. Yep. And so then you ask yourself, how many options for the first digit? So I have 10. And then how many options for the second one? Well, they said repeated, so 10 and 10 and 10 and 10 and 10. So you just multiply it. So times, 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 and it's just going to be 10 to the 6th power, right? Or you could write that out and that'll be your answer. So I think that's 1 million. Now, the next question adds restrictions. So repeated one is like the most general. There are no restrictions. And that we call the fundamental theorem of counting, or the principle of counting, because there are no restrictions. You just multiply all your options. And then permutations is, okay, now we have a restriction, no repetitions. And then combinations, like, okay, we don't even care about order anymore. So let's get rid of that too, right? So as you're going and adding more restrictions, things get smaller, right? Things get smaller. Okay, so I still have 6-digit password, 1, 2, 3, 4, 5, 6. But now for the first one, I have 10. I still have 10. But once you use one number, you can't use it again, right? So then you have to go down to your second one. Now you have 9, and then 8, and then 7, and then 6, and then 5, right? And so if you multiply that out, you get 151,200. If you really think about this, this is just 10, and we're permuting 6, 10p6, right? So if I go to my calculator, 10 math, PRB, NPR, 6, and we get the same number. So when you don't have to order everything, you can just use a permutation, right? Now, then the question becomes, how do I know it's a permutation versus a combination? Order. That's the key thing, is order, right? So let's do another problem from the review. A professor wants to award prizes for first, second, third, fourth, and fifth place in a class of 30, right? And how many ways can the prizes be awarded, assuming no ties? So if someone gets first place, that is different than getting second place, right? So there is a sense of order, some natural sense of order, right? So again, step 1 is just make your hangman. So I got 5 prizes. 1, 2, 3, 4, 5, because I have 5 prizes. So then how many students can get first place? Okay, so I have 30 students. So 30 people can get first place. But once a person gets first place, they can't get second place too. So then my second place. And then my third place. And then my fourth place. And then my fifth place, right? And then you just multiply all of these. And so if you do 30 times 29 times 28 times 27 times 26, you're going to get a really big number, 17,100,720. But again, you have 30 students and you are ordering or permuting 5 of them, right? That's what you're doing. 30 students, ordering 5 of them. So 30, math, permute, 5, and I get the same number, right? So that's permutations. Any questions so far? All right, so looking at some of the passcode problems, like a password can have 6 or 7 digits. Digits can be repeated and zeros are allowed in the front. So 1, 2, 3, 4 is a 4-digit code, and 0, 1, 2, 3, 4 is a 5-digit code. Sorry. And those wouldn't work. That means no 6-digit code will ever work for a 7-digit, and no 7-digit code will ever work for a 6-digit. So they are completely separate. So that's where that addition principle is going to come into play. You have to do one for the 6 digits and one for the 7 digits, right? So step 1 is to set up your hangman. So for the 6 digits, 1, 2, 3, 4, 5, 6. And then for the 7 digits, 1, 2, 3, 4, 5, 6, 7. So these are the 6 digit. And these are the 7 digit. Okay. They can be repeated and leading zeros are allowed, which means you have to remember this. There are 10 digits. 0 through 9. That's just something that you have to remember. And so for the 6 digit, I have 10, 10, 10, 10, 10. If it wasn't repeated, then I would have to go 10, 9, 8, 7, 6, and then 10, 10, 10, 10, 10, 10. And then I multiply all of these together. And that's just going to be 10 to the 6 plus 10 to the 7th power. And that will be 1 million. Is that a million? 1, 2, 3, 11 million. Yeah. 11 million. So this is where you have to use the addition principle because again, they don't share codes. And so what if they give us some like very restrictive parameters, right? And from a security perspective, more restrictions actually makes your passwords less secure because ultimately that limits the number of options that you can have. I guess the only argument against that is sometimes the reason they do that is because they want to eliminate super common, easy passwords that people just default to. So like 0000, like all zeros, they don't want people to use that code. So they remove like where you can repeat zeros or something like that, just because of that, because people's natural habit is to pick the easiest password. So yes, they reduce how many passwords there are, but what they're really trying to do is reduce all the easy passwords so people don't pick those. Okay. So it says that's exactly 7 digits. 1, 2, 3, 4, 5, 6, 7. Okay, digits cannot be repeated. And it must begin with an odd number. So that's 1, 3, 5, 7, 9. And then zeros cannot be used anywhere. So they say no zeros. So that means I am left with 1, 2, 3, 4, 5, 6. Forgot the 6. 7, 8, and 9. So I only have 9 options total. Okay. So it says the passcode must begin with an odd number. So this one right here has to be odd. So how many options do I have? I have 5. So then I do 5. But, okay, now it used to be 10 because I had 10 digits, but they said no 0. So now I have 9, right? Except you have to remember, it would have been 9, but we used an odd number already. So this one has already been used and you cannot repeat. So you actually are down to 8. Okay. You can't use 0 and you can't use the first number. So let's write that down. No 0 and not the first number. So that one actually starts at 8 instead. And then now I just go down by 1 because now I just can't use the previous one. So is this a permutation problem? You can make it a permutation problem, but I'm telling you right now, it's a lot more complicated to think about it like that for most students. Okay, not everyone. Some people kind of get it, but in this case, it would be 100,800. So the way you could do it using permutations is you could say, I have 5 odd numbers and I got to pick one of them. Okay, so 5 permute 1, and then from there, I have 8 numbers left, and then I got to pick 1, 2, 3, 4, 5, 6. So I got to pick 6 of them. Okay. And now that I'm thinking about that, 5 permute 1. Does that make sense? Yeah, that should be fine. So let's just make sure that's correct. So if you want to do multiple permutations, you got to do parentheses, 5, math, PRB, permute 1. Close parentheses. Again, parentheses are important for these permutations. And then, whoops, I forgot the number. Don't forget the number. If you forget, do second delete for insert. 8, permute 6, and let's see if that's correct. There we go, same answer, right? Again, you don't have to do that. That's why I tell students the hangman's better because you don't have to think about the permutations in that fancy way of like, well, how many options do I have for this one, and then I got to multiply them and then add them. If you do the hangman game, it does all that for you, and you don't got to think about it too much. Okay. Any questions so far? Okay. So how many different sequences can be formed using all the letters that are given? So you see the word sequences, the definition of permutation and multiplication, sequences, that matters. That means order, right? So how many words do I have? Letters. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, right? And so how many options do I have for my first letter? Well, I have 6. And then I can't use it again. 4, 3, 2, 1. So that's just 6 factorial. And if you do 6 factorial, 720, right? Just like that. Now, I didn't say it has to make up a word in English. It just has to be a sequence of letter. Okay, that's all. The next one, on the other hand, does cause an issue because there's repeated letters. And so part of the rule for permutations is no repetitions, okay? But what happens when you do have repetitions? Do you just give up and not do the problem? No, we actually have a technique for that. So for repetition, you divide out the repetitions. Sorry, the repeated letters. So here's the formula. It's not a too terrible formula to memorize. So n is equal to the total letters. And then a is equal to number of repeated first letter. And then b is equal to number of repeated second letter. And so the formula is n factorial over a factorial, b factorial, dot, dot, dot. So you just keep dividing out the ones that repeat, okay? You can do the hangman game with this. It's the same principle. So how many letters do I have? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 letters. So n is equal to 8. And then do I have any repetitions, right? Well, just E. So E repeats, and that's the only letter that repeats. So E repeats twice. So A is equal to 2. And so if you just plug into that formula, you get 8 factorial over 2 factorial, which would be equal to 20,160. Okay, just like that. Or if you do the hangman game, you do 1, 2, 3, 4, 5, 6, 7, 8. So then you just do it letter by letter, right? So how many options do you have for the first letter? Well, I have 8, and then 7, and then 6, and then 5, 4, 3, 2, 1. But the problem is the 2 E's, you can't tell the difference between them. So if you swap the E's, the sequence looks the same. So I need to get rid of that. So I'm going to divide it by my first repetition. So how many E's are there? There's 2 and then 1. So I can basically divide out the first E and then the second E. And then that gives you 20,160. Unfortunately, when you get more complicated problems, the hangman becomes a little bit more difficult to use because then you have to start doing stuff like that. And so it does have its limitation. And then in combinations, hangman becomes very difficult because you have to divide out a bunch of things. And so that's where we actually do use the formula, but the calculator takes care of the formula for us. Now, theoretically, you could do it another way, but this would require you to think a lot more about it. So let's just pretend that we pick all of the letters and then the very last letter is E. Well, how many ways can we pick just E, right? So like I said, or you could do 1, 2, 3, 4, 5, 6, 7, because there's 2 E's, right? So you don't need, I mean, you do need, sorry, 8, because I got to make an 8-letter sequence. So assuming that we don't pick E first, we have 8 options, 7, 6, 5, 4, 3. And then when we get to the last one, The last two are E, right? So how many ways can I pick E? Well, there's only one way because it's just E, and then there's just only one way because it's still just E. So you could do it that way. It ends up working out. It's just that one requires a little bit of like, you got to convince yourself, and I don't recommend that one, honestly. So, but if you care to think about it that way, you can. All right, and then the last one from this same problem. So now excellence. So again, first just count how many letters you have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's a total of 10 letters. And then which letters repeat? So E repeats, and it's going to be 3 times. 1, 2, 3, 4 times. And then X is 1, C is twice. And then L is twice. N is once, and I think it's all of them, right? So then the formula is n factorial over a factorial, b factorial, dot, 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 just however many times it repeats. And then we just plug in. So there's 10 letters. And then we got to divide out the 4 E's that repeat, the 2 C's that repeat, and the 2 L's that repeat. And if you plug that into your calculator, you get 37,800. Now, if you're wondering, how do I plug in factorials in my calculator? Well, I can show you that too. So 10 factorial, so 10 math, and then go to the PRB, and it's option number 4, the little exclamation point, divided by left parentheses. 2 factorial is 2. You can do like the smaller ones I would recommend doing in your head, just so that you don't have to write out the factorial because you have to go out of your way to find it. So 2, and then times 2 times 2, and then we get 37,800. Right. There it is. So nice little formula to kind of remember in case you have repeated. Typically, they don't usually ask these kind of questions on the exam because they're a little bit more challenging, but in case they do, there it is. Right. So that looks like it covers pretty much all the permutation type problems. Now we're going to want to look into combinations. So, and then that's pretty much the last thing. So combinations means, so when you're talking about combinations, we mean no order. So order does not matter. Some people like to do permutations is a, what is it called? No, so combinations is a committee. Permutations is, there was a P word that goes with it. I'll have to think about it. Like that. And then combinations, no order. So given n objects, if you want to select R objects, with no order, no repetition, and unique items, then the total combination of R objects from n total objects is, so we use NCR equal to n factorial over R factorial n minus R factorial. It's very similar to the permutation formula. It just has that extra R factorial. Okay. And then on the calculator, it's just math, PRB, option number 3. Okay. That's all it is. This one actually has several notations. The other most common one is this notation. We call that the binomial notation. That one's very, very popular. We're not really going to use it in this class, but I'm just telling you, if you look it up online, you'll see that. Okay. And let's just do some examples of these. Again, the whole goal here is like, we don't care about order. Like if I'm picking a group of 4 people, I don't care what order I pick them in. When you play poker, it doesn't actually matter how you hold the cards, right? The cards don't matter in the order in your hand. It's just what 4 cards or 5 cards you have. So let's just do a very generic problem. If you must select 6 out of 50 numbers to win the lottery, how many ways are there to do this, right? It doesn't matter if I pick 2 first or 3 first. It's the same problem. So, step 1, find total. So n is equal to 50. Step 2, find, how many you are picking. Well, I'm just picking 6 of them. And then step 3 is to plug in. 50C6, like that, 50C6 is equal to, so go to our calculator, type in 50, math, right there, and then 6, and then it's that really large number, right? 15,890,700. Not too bad. That's all combination is we don't care about the order. We just want to know how many ways can I pick something, right? And so let's look at the homework very quickly. And finish from there. So let's do the marble problem from 7.3. So a bag contains 2 red marbles, 5 green, 1 lavender, 5 yellow, 5 orange. How many sets of 4 marbles include 1 of each color other than the lavender, right? So if I have 2 red marbles, I really can't tell the difference between the 2 red marbles. So when I pick one versus the other one, like there's no ordering to them. So that's the other huge thing is when you have like indistinguishable things, that becomes more of a combination problem because you really can't order indistinguishable things, right? So effectively here, how many marbles do you want? You want 4 marbles, right? So there is an element of the hangman game in this, but I'm not going to just use a single number. So I have 4 marbles. 1, 2, 3, 4. Okay. And they say 1 of each color, but not lavender. Okay. So let's do the red marbles. I want 4, and I got red, green, yellow, and orange. That's 4 of them, right? So for my red marbles, I have 2, and I want to choose 1 of them, right? So 2, choose 1. And then for green, I have 5 of them, and I want to choose 1 of them. And then for yellow, I have 5 of them, and I want to choose 1 of them. And then for orange, I have 5 of them, and I want to choose 1 of them. And if you're wondering, why are you only choosing 1? Well, I need only 4 marbles. So 1 marble, 2 marble, 3 marble, 4 marbles, right? And if I multiply all of those together, 5 times 5 is 25, times 5 is 125, times 2 is 250. Now, here's the cool thing. If you ever have NC1, so basically NC1, it's just going to be equal to N. So if there's a 1, it's just N. And then if it's NCN, that is equal to 1. That's double equal right there. You don't have to memorize those. Your calculator can do it too. But sometimes if there's only 1, you can kind of do the math very quickly, right? And we did all the ones from the review. So all the review problems are done. And then I'm just looking through the homework to see if there's any other last little problems that I think we should talk about here. Okay, following up on this problem, so follow up. How many combinations or how many ways or how many 4 sets are there where 2 marbles are red? Okay, so 2 marbles are red. So again, how many marbles do you need? Well, I need 1, 2, 3, 4, right? I need 4 marbles. However, there is a restriction. And that restriction is the first two, or the last two, or the middle two, doesn't matter, but there's no ordering here. We need to make these red, okay? So two of the marbles are already, they're already picked for you. So that means this whole thing is actually going to become one line, and that's going to be 2, choose 2, because I need 2 reds, right? So 2 red marbles. And then for the other colors, I have no restriction, okay? The lavender restriction is gone. So then how many marbles do I have left? Well, I have 5 green plus 1 lavender plus 5 yellow plus 5 orange. And that's going to be equal to 5, 6, 16 marbles. Okay, that are not red. And so I have 16 and I got to choose one of them. And then once I pick one marble, then I got to pick another one. So then 15 choose one, like that. Okay. And there it is. And so that's going to be equal to 15 times 16, which is 300. That doesn't sound right. Let me double check. That's not right at all. 15 times 16. 240. 240. Just like that. So 2 of the marbles have to be red, so I have to choose 2 of them from 2. And so that's just 1. There's only one way you can do that. And then I have 16 left, so not red. And then after that, I have to get another marble, so like that. And this isn't the only way you could do it. In fact, a lot of these problems, some people may see it one way versus some people may see it another way. So that's always something to think about, is you're not always restricted to just one method, right? But any questions? All right, so that wraps up our review of chapter 7. Other than that, we're going to talk about chapter 8 the next day and go from there.